Welcome back, Physics 30. This is section 26-5, length contraction. So previously we spent quite a few videos looking at time dilation. And one other thing that happens with special relativity is something referred to as length contraction. So time intervals are not the only things different in different frames of reference. Space intervals, lengths, and distances are different as well, according to the special theory of relativity, and we will illustrate this with a thought experiment. So here we have a spaceship going from Earth to Neptune at a certain velocity. So the point of view of the Earth, the ship is going from Earth to Neptune. From someone inside the ship, though, leaving Earth and Neptune is approaching. Okay, so observers on Earth watch a spaceship traveling at speed v from Earth to, say, Neptune. The distance between planets as measured by the Earth observer is L naught. So that would be the true distance. What would be the distance between Earth and Neptune? Measured for the Earth, so we could say that is this. Now I also, again, you may want to grab a piece of loose leaf. You can see the derivation of the formula is relatively quick. I took a piece of paper here, so you may want to grab one too, and we can run through this as well. So Earth, the speed of the ship as measured by Earth, so distance over time, but in our case we're using L naught over delta t, so the proper length would be the distance from Earth to Neptune, what the length should be, and time experienced on Earth time. Of course that would factor in time dilation there as well. That's what that t represents. So rearranging this for the length, we get L naught is equal to v times t, and this is used later on in a substitution with an equation that happens further down the road. Okay, so if we keep on going here, now we see the point of view of observers on the spacecraft. In this frame of reference, the spaceship is at rest, and Earth and Neptune move with speed v. So of course, Earth seeing spaceship move this way is the same thing as spaceship seeing Earth and Neptune move in the opposite direction. The time between departure of Earth and arrival at Neptune is observed from the spacecraft as the proper time, just like with time dilation, because we see the Earth leaving the tail end of the spaceship and Neptune hitting the tail end. So it's like the light beam in the earlier part here. It goes and bounces off the mirror and comes back to the original location. Similarly here, the Earth and Neptune hit the same location as opposed to up here hitting a different location. So that would be the proper time for that to happen. And then they go through this here relatively quickly and they come up with this. Well, if we take a look at what happens there in terms of what the spacecraft is experiencing, so speed equals distance over time as generally stated. Now, in this case, L is going to be the length contraction that's going to be experienced by the ship, similarly to the time dilation. Now, if we look over here, the time here is proper time on the ship. So, and this will come into play later, seeing what the shortened distance really means. So if we rearrange that for L, we get L is equal to V times the proper time. And now if we look here, T naught, delta T naught, the proper time, we got that earlier with the time dilation. There it is right there, the time on the ship, time on the ship. So if we rearrange the time dilation equation, so multiply each side by the square root of 1 minus v squared over c squared, T naught, delta T, can be represented like this. So that's what gets substituted in for delta T naught over here. Okay, so we have that. L is equal to V times T naught, but since T naught can be expressed like this, we have that. And then of course I mentioned earlier that V delta T is right there, and that represents L naught, which is the proper length or proper distance. So if we substitute that from what I referred to as the Earth equation, or what's viewed from the Earth, so from up here, then we get the final length contraction equation right here. So the length contraction that will be experienced is equal to the proper length, hey, multiplied by that dilation factor, that special relativity factor, that factor of gamma. In this case it's 1 over gamma. So L naught is the proper length, or length of an object seen by observers at rest. L is going to be the length of a moving object as measured by an observer watching the object move past them. And that's where the contraction will happen. The squeezing of space, or a squeezing of an object in the direction of motion. So if we go back to here, that's how that equation is derived. So they simply jump from here to here. And of course, we can represent that as the gamma symbol there as well. So here is the final equation right there. So you can see it's very similar to the time dilation one. The only difference is, if we take a look back here at the time dilation equation, oops, there it is. It is, there, one more back here. Holy smokes, we had a lot of derivation there. Okay, so if you look here, the time dilation is equal to proper time divided by this factor, whereas with the length contraction equation, if I zoom back here, it's the length contraction is equal to the proper length multiplied by that factor. So with the other one, the time gets longer for time dilation on Earth, whereas here the length of something seen gets shorter. Length contraction. So it's an inverse of the other one. And of course, yes, we can represent this as 1 over gamma. So this is a general result of special relativity and applies to lengths of objects as well as to distance between objects. The result can be stated most simply in words: the length of an object moving relative to an observer is measured to be shorter. Now, the key thing there, along the direction of motion than when it is at rest. So perpendicular distances won't change. It has to be parallel to the motion. This is called length contraction. The length L naught in that equation is called the proper length. It's the length of an object or distance between 2 points. So bear in mind, we could be talking about the actual length of an object or the distance between 2 areas. So like over here we see length contraction with the Earth. So you can see it's kind of squished. The Earth is squished, Neptune's squished, because according to those people on the ship, the Earth and Neptune are contracting along their direction of motion, whereas here on Earth you can see the rocket is squished compared to this because it is the object that's moving. So it's contracted in the way it's moving, in the direction it's moving, whereas people on the ship see, oh, what's moving past us? The Earth and Neptune, and look at, they're contracted compared to how they regularly are. Very interesting. So again, it's the length of an object is determined by observers at rest with respect to the object. So equations 26.3 gives the length that will be measured by observers when the objects travel past them at v, whether it's the rocket ship traveling away from Earth or the planets traveling away from the rocket. Okay, so we have that we talked about. So again, it's important to note that the length contraction only occurs along the direction of motion. For example, the moving spaceship is shortened in length, but its height is the same as when it's at rest. Length contraction, like time dilation, is not noticeable in everyday life because, again, we have that factor, and it's most of the time that factor is 1, except when we have v being a very large number, again, approaching the speed of light. That's when we have this factor coming into play, and we can measure it. If you look at this example here, painter's contraction or painting's contraction. A rectangular painter measures painting again 1 meter high by 1.5 meters wide. It's hung on the side of a spaceship, on the wall on the side of the spaceship, which is moving past Earth at a speed of 90% the speed of light, or 0.90 c. What are the dimensions of this picture according to the captain on the ship? And what are the dimensions as seen by an observer on Earth looking at it? So, of course, we applied the length contraction formula, but to the person in the spaceship looking at the painting on the wall, the painting is not moving with respect to that person in the spaceship, so, of course, nothing changes. It's still 1 meter by 1.5 meters. But when someone on the Earth is seeing this spaceship move at 90% the speed of light, they would, in fact, see a contraction. And I think we'll save that for the next video because we're running out of time here. So we'll come back and take a look at that solution B, in which we will in fact use the length contraction formula.